Alright, this video I'll be talking about the pattern for dividing by 9. If you've seen the intro video to Decimology on Decimology.com, you'll probably already know this pattern, but this is what started Decimology. This was the first pattern I noticed that couldn't be explained by algebra. So, very historical, I guess. Here's the rule. I normally suggest that you pause and look at the rule, pause the video, look at the rule, try and work it out on your own. For this one, I'm just going to ask you to watch the whole video because a lot of explanation is needed to fully understand this. You probably won't understand why I put this in digit notation form unless you see the whole video or you already know the pattern. But that's the rule, and I'm going to go ahead and just drag this off to the side for now. I'm going to bring it up later so you can see, but I'm just going to show you the division by 9 pattern, and I write out these rules so you guys can kind of just have them to have, whatever, but it's a lot easier to just get an understanding of the pattern rather than try and follow a formula, because the pattern is much simpler than this makes it look. This is just a neat way of writing it out with notation. But let me get started. Alright, I'm going to take a number and divide by 9. And I'm going to start off with a simple example. If I go in the harder numbers for this pattern at least, you'll start seeing digit notation pop up. But for now, 123 divided by 9. Alright, I can go ahead and tell you the answer is going to be 13.6 barred using the pattern. The cool thing about this pattern is it lets you do it in your head really fast. But let me go ahead and get started. For the first digit, you're just going to take the first number and you'll add all the previous numbers for each next. Every time you solve for a digit, you take that number and add all the previous numbers. So 123 is the same as 0.000123.0000, and the way I notate that is just 0, 0, 0, and I put a bar on the top left corner saying that there's an infinite number of zeros this way, and then we reach 1, 2, and 3. Our decimal point is 0, 0, 0, and a bar here. So there's an infinite number that way. So I just do a reverse bar to notate that there's an infinite number of previous zeros. And that's only important when you know that you're adding. You're not really just taking this 1 and putting it here, but you're taking 1 plus all the previous numbers. So 1 plus 0 plus 0 plus 0 plus 0 plus 0, which happens to be 1, but it's just for specification purposes. So let me go ahead and do that. 1 plus 0 plus 0 plus 0 is 1, right? Next digit, we are now on the 2. So 2 plus 1 plus 0 plus 0 plus 0. That's 3. And then 3 plus 2 plus 1 plus 0 plus 0 plus 0. 6. Alright. And then we have 0.000. So 0 plus 3 plus 2 plus 1 is still 6. So our next digit is 6. Right? And then 0 plus 0 plus 3 plus 2 plus 1 is another 6. So we're going to have barred zeros, and in turn that's going to give us barred 6's, right? So we have 1, 3, 6, 6, 6, 6, 6. And you're going to, it's kind of hard to distinguish now, but the general rule is if you have a 3-digit number, right, then the answer is going to be 2 digits, then your decimal point. If you have 4 digits, then it'll be 3 digits, then your decimal point. 5 digits will be 4 digits, then your decimal point. So it's always just 1 less in the answer. And that's just because 9 is so close to 10, and 10 moves the decimal point over. There's probably an exception, but you can usually figure it out. I may come up with a better rule for explaining how to figure out where the decimal point goes in the answer later on in the future. But as of now, 13.6 barred is our answer. And if we go to the calculator, 123 divided by 9, you'll see it's 13.6 barred, which is what we said. Let me give you a harder example, because I know some of you probably have already paused the video and tried this out on your own and then screwed up and wondered, hey, what did I do? So if not, I'm glad you kept watching, because now you'll get to see and you won't make this mistake, hopefully. So let's take a number where when you add them, you're going to go over the barrier of single numeric digits. So you might have a single digit that's like greater than 9, maybe a 13. So probably should make this like 786 divided by 9. And just for demonstration purposes, I'll make this 786.5 just to show that this doesn't have to be an integer. This works for all numbers. So 786.5 divided by 9 is, so we'll start out, our first decimal place will be 7. Alright, then the next one's going to be 8 plus 7, which is 15. So we're going to write that all in one. Alright, this isn't 715, this is 7015. It's 2-digit number so far, not 3 digits. This is digit notation if you haven't watched that video. Then 6 plus 8 plus 7 is 21. And then 5 plus 6 plus 8 plus 7 is 26. And then 0 plus 5 plus 6 plus 8 plus 7 is also 26. And then the next one's going to be 26. And we get 26's forever. So now we need to convert this answer to standard digit notation. 26, we'll take the 26 over here and we'll carry the 2 over into here. So this becomes a 6 over here, right? And the 2 the 2 gets carried over to 26, so now we have a 28, right? And I'm just gonna not write this 6 for now. The reason I'm not writing this 6 is because it's not really a 6, because there's another 26 after that we have to carry over. So this is a 28 also, and it keeps going forever. So I'll just put the bar here where we have it, so you'll see that this is the number that's actually going to be barred over here. We got to carry this 2 over now because we still only want 1 digit here. So this 26, we're carrying the 2 over to this 26 now. So we get rid of this 2, we carry it over, right? And we'll carry it into this 26. So now this becomes 28. And once again, we have to get rid of this 2 and carry it over to this 21 over here. So 21 plus 2 is 23. And then we have to carry this 2 over to the 15 right here. So 2 plus 15 is 17. And then we have to carry this 1 over to the 7. So 1 plus 7 is 8. We have a 3-digit before the decimal, right? So there's only going to be 2 digits before the decimal here. So 87.388 barred. So if the pattern works, 786.5 divided by 9 should equal 87.388, and so on. So 786.5 divided by 9, let's plug that in. 87.3888888. This is a non-algebraic pattern as of now. Let me go ahead and leave this up real quick and just revisit the original rule. I'm going to zoom in because if you're watching this in a low-res version, you probably can't see some of the tiny stuff, such as log base 10 of n when I'm out here. Maybe you can, but just for the sake of it. Alright, x divided by 9 equals y. So we have 786.5 divided by 9 equals 87.3888. So any digit, these are the digits, right? Any digit in our answer, which is y, this is our answer. So any digit in there is this. So for example, if we want to find psi y 10, alright, then n is 10. So we're going to take the, this is 10, right? So we're going to take the sum, the infinite sum of z equals log base 10 of n. Log base 10 of 10 is simply 1, so this will be the infinite sum z equals 1 of psi of x. X is the number being divided by 9, so psi of x, right, of 10 raised to the first power, so of 10. So the tens digit place of x, which is 8, right? So we're going to write down an 8. And then, since this is infinite, we're going to do it forever. So now z was 1, right? So now it's going to become 2. That's how sigma notation works. So psi of x, and then it's 10 raised to the second, so it's the 100. 100 places 7, so plus 7. And then now z becomes 3, and the thousands place of x is 0, so 8 plus 7 plus 0 plus 0 plus 0, and so on, will get us 15. So the tens digit place of the answer, which is y, right, should be 15. And if we go back to the tens digit place, which is right here, it's 15. So that does work. You might be like, well, why isn't it 7? And that's because, oh, I think I wrote the rule wrong now that I think about this. Tens digit place should be 7. Alright, so this is just, my rule is just off a little bit. It still works. It should be saying, let's see, this should be, oh, I have 100 here. Alright, so this should just be n over 10. That's all. I'll change that in a second. But this is actually giving one less digit place as the answer. But alright, yeah, that still works. You might be saying, why isn't it 7? So the reason is because this is without carrying over since we're adding. So that's why I notated the rule with digit notation here, so you know that I'm not talking about the standard digit notation, but the actual single digit notation being 15. Let me go ahead and clear all this and fix the rule real quick. I'll bring it up full screen also so you guys can all see. Alright, here's the rule, and it should say, this is a simple, quick fix. This should say n divided by 10. Oops. N divided by 10. So here's the actual rule. So I hope all of you took my advice by none of you pausing the video at the start and letting me explain this all, because it turns out my rule was off a little bit, but this is the real rule. This will work, and I hope this was a cool video for you. I hope you can learn about division by 9 now from this, and maybe this rule will go down in history, who knows. But this is the one that got decimology started, so it's pretty important to me. And now, just for fun, I'm gonna do some head math using that rule. So I'll start off with like 134 divided by 9. Alright, so it's gonna be, since this is 3 digits, it's gonna be a 2-digit answer, right? The first one's gonna be 1, the second one's gonna be 3 plus 1, so that's 1, 4, and then 4 plus 3 plus 1, which is 8, and then 0 plus 4 plus 3 plus 1, which is 8 again. So we're gonna have 1, 4, 0.888888, 14.888, 14.888. So let's do some of these in our head, shall we? 233 divided by 9 will be 25.888888. Alright, so let's just enter a random number. 142.12 divided by 9 should be 15.78. Alright, then I gotta carry over. So 15.79. 10 carries over 1. 15.791 barred? Yeah, cool. So the larger the numbers get when you add them, it does take a little bit longer in your head, but it's still fun to impress your friends with smaller numbers, such as 25 divided by 9. You know that's going to be 2.7 barred. Or 36 divided by 9 is 4. Okay, that one was that simple. Oh, that's a good point. I'm glad I brought that up. 36 divided by 9. or something that is divisible already by 9. So a simple example would be 18 divided by 9. Everyone knows 18 divided by 9 is 2, right? So our pattern would lead us to believe that it will be 1, right, for the first one, and then we're going to have 8 plus 1, which is 9, and then 0 plus 8 plus 1, which is 9, and 9, and 9, and 9, and 9, and 9. So 1.9 barred. And this is technically true. 1.9 barred is equal to 2. And this has to do with asymptotical graphing. And a simple explanation I can offer to those who haven't heard of this before is basically 1/3 equals 0.3 barred. That's without doubt. So if we multiply both sides of the equation by 3, we have 3 times 1/3 and 3 times 0.3 barred. Alright, on this side we can cancel out the 3's, so we're just left with 1, and then 3 times 0.3 barred is 0.9 barred. And most calculators, if you enter this in it, it's probably just going to give you 1, and that's because 0.9 barred equals 1. So, back to the example I was saying, 18 divided by 9 is 1.9 barred, which is 2. So if you are trying to do head math, don't forget that if you write 0.9 barred, just replace it with 1 greater. So, alright, I'll see you guys later. If you have any questions or additions, or if you figure out more about division by 9 or figure out an algebraic explanation, please email me at this address. And as always, Decimology.com production. I hope you enjoyed it. I hope you learned more. And until next time, I'll see you.